Okay, so we're given the following matrices, A sub 0 through A sub 5, and each one has these given dimensions. So we don't record those dimensions that are the same, so this is exactly D0, and D1 is 35, D2 is 15, D3 is 5, because we know that these dimensions will be the same, because otherwise we wouldn't be able to multiply those two matrices together. So we've got our values D0 through D6, representing the dimensions of matrices A0 through A5. Now we're going to start to fill in our n table. This represents the number of scalar operations which are required to multiply all of the matrices starting with A sub I, where I is whatever value we've got over here. This is our starting point, and going all the way up until A sub j. This is our ending point, whatever value we have on the right. So we're going to fill these diagonals kind of from left to right, going down. Now, when the starting and the ending point is the same, all of these values are 0. So this is, for example, here, this is saying how much does it cost to multiply starting with A sub 2 and going all the way up until A sub 2, which is just the matrix A sub 2. So we have nothing else to do. This doesn't cost anything. Whereas here, this is saying we're starting at A sub 4 and we're going all the way up until A sub 4. And we already know what the matrix A sub 4 is. We don't have to multiply anything to get it. So the number of scalar operations that it takes is 0. Now, separately, we're also going to record a k table. So we'll see this filled in a moment, but this will be keeping track of where that last index was, where we multiplied in order to get whatever we had put in these cells. So once we start building up larger chains, we'll have maybe here was our last multiplication, meaning that this was how we had parenthesized them. So k is just recording where did we have our last multiplication. We tried all of these possible values and one of them gave us the least number of scalar operations. If that was 3, for example, A sub 3, then we're going to record that k is equal to 3 at this starting and ending index in our k table. So you'll see what I mean in a moment here. So let's move on now. We've already filled in all possible chains where we have just one matrix to work with. Now we're going to fill in everything where we've got 2 matrices to work with. And in that case, we don't have any options of where our last multiplication could be. We only have one choice. So in this case, we have starting with A sub 0 and going up until A sub 1. This is A sub 0 times A sub 1. So we have the cost to form the left matrix, which is what we've recorded here. The cost to form the right matrix, which is what we've recorded here. Again, we don't have to do anything to form A sub 0 or A sub 1 because we're given those already. Plus the product of their dimensions. Now we know A sub 0 is a 30 by 35, and A sub 1 is a 35 by 15. This was part of what we were given. So we just multiply those values together. We're left with 1500. So we record that value, and in our k table, we record where did that multiplication occur. In this case, it occurred immediately after A sub 0. So we record 0 to indicate right after this index is when we multiplied. Okay, now for the next cell. So now this is starting at A sub 1 and going all the way up until A sub 2. So we're just multiplying A sub 1 times A sub 2. And again, we have the cost to form the left matrix, which was nothing, the cost to form the right matrix, which didn't cost us anything, plus the product of their dimensions. A sub 1, we are given, is a 35 by 15 matrix, and A sub 2 is a 15 by 5 matrix. So we record that value of, this is how many scalar operations it took. We keep that in our n table. Then in our k table, we record where did we do that last multiplication. It should be a 5. Where did we do that last multiplication in order to even get this number that we started in our n table. So our last multiplication here occurred immediately after index 1. So in our k table, if we're multiplying A sub 1 and we're going up until A sub 2, the best place where we should multiply is right after A sub 1. Okay, in the next cell, we have A sub 2, multiplying that all the way up until A sub 3. So this is starting to get a little repetitive here. So we've got how much it costs to form the left matrix, which is just a sub 2. We know this to be nothing. Plus how much it costs to form the right matrix, which is just a sub 3, didn't cost us anything, plus a product of their dimensions. So we record whatever that total is, put it in our n table, and then in our k table we record where did that multiplication occur, which gave us this best solution. And that multiplication here had occurred immediately after a sub 2. Now usually when I show this during class, it's at this point that students tend to understand, they start to see the pattern. So I'm going to skip ahead a few slides. If you're lost here, I have the entire solution posted on the PDF slides, which are available to you, so you can walk through each step. But I think this starts to get a little more interesting when we have larger chains to work with. So I'm going to skip ahead a few slides, assuming, I wish I could see your faces right now to confirm this, but I'm assuming at this point that you understand how to form these smaller size chains. So how we would form the next cell and how we would form the next cell as the product of those dimensions. So working with that assumption, let's try and fill a few cells in the next diagonal here. So we've already figured out this gave us all the ways in which we had everything along this diagonal. We had just one matrix to work with. Here we had 2 matrices to work with. Now we're going to look at chains of 3 matrices. So just working from the top, now we're starting at a sub 0 and we're going all the way up until a sub 2. So we have a sub 0 times a sub 1 times a sub 2. And now we've got 2 choices, 2 different ways where we could multiply. In the first one, here k is equal to 0. Our last multiplication occurs right after a sub 0. And here k is equal to 1. Our last multiplication occurs right after a sub 1. This is right after our right parentheses here. Now which one we should choose? It depends. So let's calculate for them both. We have the cost of, let's do for when k is equal to 0. We have the cost of forming the left matrix, which we know doesn't cost us anything. This is n 0, 0, plus the cost of the right matrix, how much it costs to build it, which is n 1, 2. So that's this value here, plus the product of their dimensions. So what are their dimensions? We know the dimensions of each individual matrix, but you can use them to figure out the dimensions of this larger right and left matrix, for example. So a sub 0 is a 30 by 35, a sub 1 is a 35 by 15, and a sub 2 is a 15 by 5. So it's these outer dimensions that are most important. This is what our resulting right matrix will be. So the product of those dimensions is this, and we're left with 7,875. But we can't stop there. We don't know if this is the best one because we could have instead multiplied here. So calculating for this one now, we have, if we were to instead split right after a sub 1, then how much it costs to form this left matrix. This is, I'm going to circle that now, 15,750, plus the cost to form the right matrix, plus the product of those dimensions. Notice that the left and the right dimension are going to stay the same. The only thing which will differ is this inside one, which changes based on where we did our last multiplications. We have this is a 30 matrix, a sub 1 is a 35 by 15, and a sub 2 is a 15 by 5. So the last part is the product of those dimensions, 30, 15, and 5. Now between these two values, we take whichever one of these was smaller, which is this one here. So we record that smallest value in our n table, and we record in our k table in the same cell what k value gave us that small value. And in this case, this is when k is equal to 0. Okay, let's do another example of that in the next cell. So now we have, starting with a sub 1, going all the way up until a sub 3, we have 2 different ways where we could calculate that. Either we split right after a sub 1, or we split right after a sub 2. So in this case, k is equal to 1, and here k is equal to 2. Now if we do the first way, then we've got how much it costs to build the left matrix, just a sub 1, plus how much it costs to build the right matrix, plus a product of their dimensions. So a sub 1 is a, let's put it up here, is a 30 by 35, and A sub 3 is a 5 by 10, so we've got this resulting right matrix will be a 35 by 10. So our total there is 6,000. But if we were to split instead right after A sub 2, we'll have how much would it cost to do it this way. We have how much it costs to form the left matrix, plus how much it costs to form the right matrix, plus a product of the dimensions. So we know still, 35 and 15. We know that A sub 1 is a 35 by 15, A sub 2 is a 15 by 5, and A sub 3 is a 5 by 10. Okay, so now between these two values, we've got, this is the smallest value, so we record this smallest value in our n table, and we record what value of k, either in this case 1 or 2, this is where our last multiplication occurred, which gave us this minimum value, and this was right after A sub 2. So we record 2 in our k table. Okay, again, I'm going to skip the next couple examples because they are the same in order to fill in these two cells. This is the same value. And I'm going to move to one of the next cells. So let's say we've already filled in this table this far. And again, the slides are available online if you want to go through this step by step if you got lost in any one of the previous examples. But let's say we're filling in this cell next. So this is, we're starting at A sub 1 and we're going all the way up until A sub 4. So A sub 1 times A sub 2, A3, and A4. And now we've got 3 different ways where we could do this last multiplication. In this case, k is equal to 1. Here, k is equal to 2. And here, k is equal to 3. Which one we should do? We have to calculate for all of them how many operations this takes and then pick whichever one uses the least operations. So in the first case, and let me show the dimensions of, just write down the dimensions of each matrix here to make it easier for us to later see what their dimensions are. So A1 is a 35 by 15, A2 is a 15 by 5, A3 is a 5 by 10, and A4 is a 10 by 20. Okay, we're going to reuse this for each of these problems. Now, if we split right after A sub 1, then we've got how much it costs to form the left matrix plus how much it costs to form the right matrix, A sub 2 times A sub 3 times A sub 4, plus a product of their dimensions. What their dimensions are, this is A sub 1, which is a 35 by 15, and this larger right matrix, its dimensions are just the outer dimensions here, the left one for A2 and the right one of A4, which is 15 and 20. And plug this into a calculator, we have 13,000. To form the next one, here we've got how many scalar operations this will take. This is how much it costs to form the left matrix, plus how much it costs to form the right matrix, plus a product of their dimensions. In this case, this is A1 times A2 will be a 35 by 5 matrix, and A sub 3 times A4 will be a 5 by 20 matrix. This is what we've got here. And then lastly, if we were to split at this index right after A sub 3, then how much does this cost? We have the cost to build our left matrix plus the cost to build our right matrix plus a product of their dimensions, which is a 35 by 10, this is that dimension 10, by 20. Okay, so figuring out among all of those which one has the smallest value, our resulting value here, and we know that this gives us the smallest value. We record this in our k table, and we record in our n table, and we record where did we do that last multiplication. This was right here. This was right after A sub 2. So we record 2 in our k table. Okay, we'll do just 2 more examples here. If you get the idea, you can skip to the end, but this is worth showing a couple more things here. Okay, so now let's say we've already filled in all of the previous cells and we're working on this one. So we want to multiply starting with a sub 1 and going all the way up until a sub 5. And we've got a few ways we could do that. Either we split right after a sub 1, in which case here's our k value, 1, 2, 3, or 4, based on where our last multiplication occurred after which subindex. And we've got 4 options of where we could split, of what possible k values there are. And in each case, we're going to figure out, we're going to do this kind of one after the other, how much it costs to form the left matrix plus the right matrix plus the product of their dimensions. We know what their dimensions are because this is given here, so if we fill them in, we've got a sub 1 is a 35 by 15, a sub 2 is a 15 by 5, a sub 3 is a 5 by 10, a sub 4 is a 10 by 20, and a sub 5 is a 20 by 25. So if we split here, we'll have a 35 by 15 matrix and a 15 by 25 matrix, because this is where our starting and end parentheses are. So that's how we get 15 and 25. If we were to split here, we have what it costs to form the left matrix, plus what it costs to form the right matrix, that's what we're left here, plus the product of those dimensions, which is 35 by 5 by 25. Or if we were to split right after index 3, we've got the cost to form our left matrix plus the cost to form our right matrix plus the product of their dimensions, which is a 35 by 10 matrix and a 10 by 25 matrix. Or lastly, if we split right after a sub 4, this would be how much it costs to form our leftmost matrix plus our rightmost matrix plus the product of their dimensions, which is a 35 by 20 by 25. Okay, so we plug all those into a calculator. We find that this gives us the smallest value compared to the other ones. So we take that minimum value, put it in our end table, and take which k value gave us this minimum value. This is if we were to split right after a sub 2. So we record 2 in our k table. All right, last one. So if we start at a sub 0 and we go up till a sub 5, we're left with the following options. Again, this is, you'll notice this is kind of reading first from the first cell here and then starting with the first cell kind of going down. So this is cost to form our left matrix plus the right matrix plus the product of their dimensions, left matrix plus the right matrix plus the product of their dimensions, and so forth. And then we can figure out of each of these which gives us the smallest value. This is that smallest value which we record, and then we record which k value gave us this smallest value. In this case, k is 0, here k is 1, k is 2, 3, and 4. This is just right where immediately before our last multiplication occurs, so this helps us reconstruct that parenthesization. And in this case, we have when k is equal to 2. This gave us the smallest value. Okay, so if you missed anything, go back through the slides that I posted online and you can step through each one individually. If you have any questions, you can also post on Piazza, but we're not done yet, actually. So far, we've just filled in our n table and our k table. Okay, so that means that if we were given these matrices of these dimensions, the least number of scalar operations that it takes to multiply them all together is 15,125. Okay, but our goal here was to find a parenthesization. So we need what parenthesization coincides with this many scalar operations. This is where our k table is going to come into play. So we need to now reinterpret this k table to figure out what does it mean, how should we parenthesize this chain of matrices. So I have the solution here, but let me kind of one by one go through how did we get to this parenthesization. So we will check if we start at a sub 0 and we go to a sub 5, this is our entire chain of matrices. Where should our last multiplication occur? This is at index 2, which means our first step will be, okay, here will be our last multiplication right after a sub 2, which is given by this value here. Now we've got a few smaller chains of matrices. This one starts at a sub 0 and goes up until a sub 2. This one starts at a sub 3 and goes up until a sub 5. So for each one, we're going to figure out how we should parenthesize it. Well, if we start at a sub 0 and we go to a sub 2, this is the following. Starting at a sub 0, going till a sub 2. This tells us that our left matrix, we should do our last multiplication right after a sub 0. So this is how we get this parenthesization. And for our right matrix, our last multiplication should occur at, if we start at a sub 3 and go up until a sub 5, so we're starting at a sub 3, we're going up until a sub 5, our last multiplication should occur after a sub 4. So this is where we get this next parenthesization. And we could repeat the same process for example, a sub 3 and a sub 4, but as we saw before, there's really only one way that we can multiply these together because we don't have any option of where we could put our multiplication. So there's really 3 steps to this. 1, fill out the end table. As you're going along with this, also, secondly, fill out the k-table. And then when we're finished, this k-table is really what gives us how we can construct this optimal parenthesization. Okay, if you have any questions, post on Piazza. We're going to see how we can take away from this, what parts of this word dynamic programming, which gives us that general kind of dynamic programming technique.